Okay, so nuclear chemistry. Now, there's a lot of different aspects of nuclear chemistry. You probably heard of nuclear reactors, atomic bombs, and things like that. So basically, the idea of nuclear chemistry is, I mean, we've learned conventional chemistry where you have molecules breaking apart to form new molecules, and they reform by their bonds switching around, basically rearranging. For nuclear chemistry, it's a little bit different. Instead of the molecules breaking apart, we're actually going to have atoms breaking apart and reforming other atoms. So there's different ways radiation could occur, and the main type is ionizing radiation. So what happens is most of our electromagnetic radiation is ionizing, so it makes atoms into an ion, but and that's ionizing. So you remove electrons off of an atom using a lot of energy, and then that causes ionization. But then you could also have, this can cause free radicals, which I'll talk about in a second. But radiation could also lead to the nucleus that's why they call it nuclear chemistry. And like nuclear reactions, right? Where that involves the nucleus. So the nucleus could actually break apart. The protons and neutrons can come out of it, and it could become two different elements even. So one bigger element could break apart into two other elements and also emit radiation, electromagnetic radiation, and like really high frequency radiation at times, like gamma rays. But something else that's bad that radiation produces are these things called free radicals. And it's the product of this ionization. So when things become ions, that's normally, I mean, it makes them more reactive, right? They have a charge. But when you have oxygen, for example, so talk about oxygen real quick. Get the pen out. So you have oxygen. If you draw the dot structure for oxygen, it has 6 electrons, right? If you have ionizing radiation come in, kicks off one of the electrons, you're going to end up with oxygen with 5 electrons. When oxygen partakes in its usual bonds, you're going to end up with, it likes to have a double bond, say a double bond to something else, let's say carbon. You're going to have a lone pair of electrons, which is fine, but then you have this lone electron. This is called a free radical. And it's really reactive, extremely reactive, and it's very bad for the body. Now, these are called oxidative radicals or oxygen radicals, and they're very bad. They react with everything basically. So they can react with your DNA, and they could disrupt either your proteins, your DNA, and then it could mess up your DNA replication. It can make cancer cells. It's just very bad. It can lead to mutations, etc. So our goal in life is to limit this radiation by basically eating healthy, eating antioxidants, right? Antioxidants are things that can actually quench these oxidative radicals, because we all have a certain level of these oxidative radicals in our body. But as we age, they increase if we are partake in bad habits, such as drinking a lot of alcohol and eating bad food, things like that, not exercising, then these oxidative radicals begin to build up, increasing our risk for certain diseases, and really every kind of disease that's associated with just not a good lifestyle. And it's usually formed by mutations that are the product of these oxidative radicals. So antioxidants are good. Exercise can reduce them as well. And living a cleaner lifestyle could reduce them. But anyway, so radiation itself, I mean, like I just said, it can damage tissues such as white blood cells, bone marrow. Those are fast growing tissues. And also it can disrupt DNA and cause the mutations. Now, here is the sources of DNA, or not DNA, of radiation in our lives. And most of it is natural radon, which isn't too bad for us. I mean, we live with it all the time. Then you have some cosmic rays, which are due to like solar flares and things from the sun. And then you have radiation inside our body, caused just by different isotopes, but that's not really that dangerous. Rocks and soils could have radioactive isotopes. Medical X-rays, that's very important. That's probably the larger percent of our our bad forms of radiation, or very high energy radiation. So if you haven't, let's say, so I went to the dentist last week and I had to get an X-ray, right? So every so often you go to the dentist, you just get an X-ray of your teeth to see how they're doing, see if everything is fine. So he put this big lead shield over my chest, right? And that's just so it blocks the X-rays from entering my chest area where they could cause mutations in my heart or lungs. They can disrupt processes. So you want to limit the amount of X-rays you have. Nuclear medicine, things like iodine and everything like that. So there's other forms as well. So something else that's important and interesting and relevant to our lives is cell phone use and radiation. So maybe I think when we had the radiation lab, I'm not sure if we had it, but I forgot, honestly. Maybe I talked about radiation and cell phones, but so here is the data, right? So you want to know what the deal is. I'm sure many of your parents have said, cell phone, don't sleep with your cell phone next to your head. It can cause brain cancer, blah, 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 et cetera, like that, right? So that's not true. We don't know that. We have no evidence suggesting it's true. But we do know that cell phone usage near our head increases a little bit of our brain activity in certain spots. Here's the frontal lobe, and there's a little bit of increased brain activity when the cell phone's on versus when the cell phone's off. Now, what that suggests in terms of cancer and diseases, we don't really know. So I'm going to pull up, here's this, the cancer organization, American Cancer Society, what the studies have shown. So studies have shown that in most cases, neither study provides enough evidence on its own to show if something causes cancer in people. So researchers look at both lab, okay, whatever. But what they figured out is that several studies have looked at possible links between cell phone use and tumor. Most of these studies have focused on brain tumors. Many of these have been case control studies, okay, whatever. They said mixed results. Some have found possible link, others have not. So it's really in the air. There was a study done in England where they have like a 3% increase in brain cancer, and then that went viral and people were like, oh my God, but that was an insignificant percentage. And that could be due to other things that are uncontrolled variables that are in the person's lifestyle. So we don't know. But I think based on the radiation type that it doesn't really have an effect. And here's what I mean. So I think I went over this when we went over radiation lab, is that where are cell phones located on the ionizing radiation spectrum? They are located right here. So in between microwaves and radio waves, which both have proven not to cause cancer. They're not dangerous to us. They're lower frequency. So just keep that in mind. It's not as bad as you think, but just to be safe, it would be good to not have your cell phone on by your head when you're sleeping every night. So that's another thing to keep in mind in case the data is wrong. Okay, so the big concept of what we're going to learn today is nuclear equations. So these are very similar to chemical reactions, but they have the breaking apart of nucleuses involved instead of breaking apart of molecules. And they involve the atomic number and the mass number. So if you recall, atomic number is the number of protons in an atom. This is all very important. And also, this information is from a long time ago, a couple of months ago, but it's very important for the final exam, and it carries on throughout the course. So you need to know all this stuff. And the mass number is not the average atomic mass. The mass number is the mass of an isotope. So for example, if you have oxygen 16, so this is oxygen, this is the nuclear symbol for oxygen. In this case, the isotope for oxygen is a mass number of 16. So mass number. 8 is the atomic number, as we should know, that it has 8 protons. Another isotope of oxygen could be oxygen 15. So this is still oxygen because it has 8 protons, but in this case, the mass number is 15. It's a different isotope. We know the average atomic mass is 15.997 based on the periodic table. That's different. That we use that to calculate the molar mass. We're not using mass numbers to figure out molar mass. These are individual masses of the isotopes. So in this case, for oxygen, there's 2 isotopes, 116, 115. For nitrogen, you could have 14 and 15 as well. So but these are different isotopes. So just keep that in mind. Okay. So here are the nuclear symbols. There's a lot of stuff going on here, but you already know half of them. So these are the symbols we're going to use in these nuclear reactions. And the first one's a proton. The proton you might see as symbol is P, and we know what a proton is. It has a mass number of 1, and it has a proton number of 1 because it's a proton. It's only one proton. And alternatively, we call a proton hydrogen, right? Because when hydrogen has 1 proton, 1 electron. When we kick off that electron and it becomes ionized radiation, it is just the proton left over. So hydrogen is a proton in essence when it's a positive charge. The next one is the neutron. The neutron is symbol N. And we know the neutron has a mass of 1, but it has no charge. So we're going to write 1 and 0. So again, the top number represents the mass. The bottom number represents the atomic number. Okay, then we have an electron. So an electron is E minus, which that makes sense to us. But what about this B minus? This is actually not B, this is beta, the Greek letter beta. Now what that means is a beta particle. And we'll be going over this in the next couple of slides, but just to give you an overview, the beta particle is a high energy electron. So usually emitted from some kind of nuclear reaction where you have electrons that are at higher energy than normal electrons. These are called beta particles. So you can have beta minus or E minus. They're the same thing. If you're more comfortable with E minus, sure. But if you see beta minus in an equation, you should know that it means basically a high energy electron. And the symbol, we know the electron has basically no mass. So the mass number is 0. And the atomic number we can say is -1 because protons are 1. The electrons are the opposite of 1, which is -1. So they oppose a proton. But then you can actually have this type of, those are the ones we know. So these are the 3 that we understand. Then there's 3 new ones or 4 new ones. And they are these ones. So you can have a positively charged electron. And it's just another form of nuclear radiation that could be emitted from a nuclear reaction. And this is called the positron. So the positron is very similar to the electron, but it's positively charged and it's high energy. So that's it. It's E plus, beta plus, and the symbol is 0 plus 1 instead of 0 minus 1. So it's kind of like a proton with no mass, or think about it as a positive electron. That makes it positive electrons easier because it's electron, which we know is negative, and then positron, which is the positive version of it. So the word makes it easier to understand. Any questions on that one? Okay. Next one, alpha particle. So an alpha particle is another form of radiation that could be emitted or could be taken in by a nuclei. And we use alpha as the symbol, usually. Also, what it is, the definition of it is a helium atom. So we've already talked about hydrogen atoms being used in nuclear radiation, but now we have a helium atom is also a type of particle that can be emitted. And then the helium is called an alpha particle when it's at high energy. So the helium that's in your balloon is not an alpha particle. It's just helium. If you take all those helium atoms that are in the balloon and you shoot them through a laser, then, like a helium beam, then in that case, they'll be alpha particles because you're giving them enough energy to move to be a form of radiation. So it's a little bit different than a helium atom. It's just higher energy. And the symbol is very similar to a normal helium atom where the mass is 4 and the proton number is 2. And then we can use alpha or we could use HE. So keep those in mind. Those are the same thing. Okay. So next, a beta particle. So first of all, is there any questions on alpha particles? No? All right. Next, beta particle. So a beta particle is the same thing as an electron, but it's just a high energy electron. So if you look at between electron and beta particle, the symbols are exactly the same thing. So just think they're exactly the same, but an electron is not a beta particle all the time, but a beta particle is always an electron. So beta particles are basically high energy electrons, like we said before. So then you have gamma rays. So gamma rays are the highest energy form of radiation, or the highest frequency, same thing. And they are denoted by this gamma. So gamma looks like a cool looking Y. The way I draw it is like this. So that's how I draw gamma. So I just go loop like that. And in terms of the mass and the protons, it doesn't have any. So it's such a high radiation, such a high energy. It doesn't have any mass really. It doesn't have any charge either. So why is it important? If we put this in an equation, the numbers wouldn't do anything, right? Exactly. But for something to have emitted gamma particles or gamma rays, it's important for us to denote that in the equation because that affects the environment. So these gamma rays are the highest energy radiation that can cause cancer and things like that. They go right through your body. So it's very harmful. Okay, so we're going to cover these in detail more in the next couple of slides, but there's any questions on this overview chart? Or are there any questions? No? All right. Okay, moving on. So we kind of went over this already, but here are the forms again. The major types of radiation that are going to be emitted from the nuclear reactions. And you have alpha, beta, and gamma. Now, alpha particles, we already talked about, mass is 4, the charge is +2, or the proton number is 2. The identity is helium-2+, so it's an ionized helium, so it's faster and it's more energy. And the velocity is 0.1 times the speed of light. That's very fast. But compared to other forms of radiation, it's not that fast. So alpha is the weakest. So the weakest form of radiation. So it could be blocked by like wearing a shirt or just a piece of paper, really anything could block an alpha particle. So that's what I mean by penetrating power. Their penetrating power is very low. Then you have beta particles, which are in the middle. They have the mass of an electron because they are an electron, but they're higher energy. So here's the electron, and their velocity is about maybe a little bit less than 90% the speed of light. So 0.9 times c. C is the speed of light. So they're very fast, but they just have moderate power. So such as if you have beta particles from the sun and UV rays, then wearing a couple layers of clothing or sunscreen might block them. So there's moderate penetrating power. Then you have gamma rays, which are the highest, or not the strongest. The strongest form of radiation. They are very light, they are very fast, and they're high energy photons. So gamma rays are just really fast photons that move at the speed of light, because all photons do. And they are extremely high penetrating power. They can go right through our body. Light cannot go through our body, because visible light at least, because if you shine a flashlight on somebody, the light doesn't go through their body. We're not transparent. But to gamma rays, we are transparent. Those can go right through us. But they're so high frequency that it's beyond the visible light spectrum and we can't see them. So they can cause cancer and DNA damage and things like that. Does anybody have any questions? No? All right. Okay. So now we're going to get into the first type of reaction, which is called an alpha decay. Now, an alpha decay, by the name, means alpha particle. So if we recall, an alpha particle is a helium atom. So we'll put He, 4 and 2, like that. So it's a helium. And decay. Whenever we have decay, that means it loses the particle. So we'll put decay means loss. So the reaction is we're going to have, and in this case, this example, we'll have radon, which has this isotope of radon has a mass number of 222 and an atomic number of 86. That's the case, and it goes through an alpha decay. That means a alpha particle is coming out of the nucleus, and what's being left over is polonium 218. So numerically, these are very easy to do. So here's what the equation would look like. So here's a nuclear equation. Oh, that's a bad circle. I won't circle it. You can just see it on the bottom. Okay. So you see the radon 22286. So its atomic number is 86. The mass is 222. If we say it's going through alpha decay, automatically the reaction goes, and we know we have an alpha particle. So if that's the case, then what will be left over is whatever added to 4 gives you the starting material of 222. And whatever added to 2 gives you 86. So you're, in essence, all you're doing in these equations is 2 additions. So, you know, when you add things together, addition, you're doing 2 of them. One for the top number, one for the bottom number, and that's it. So if you have an alpha decay, you have 222 equals 4 plus 218. That's why it's 21884 polonium here, because the top number, 218, plus the alpha particle 4 equals the starting material 222. And then same thing on the bottom, helium, the proton number of 2 plus 84, that's 86. Radon, 86. That's the proton number. So this is an alpha decay. And every single one of these type of nuclear reactions works the same way. You're doing 2 additions, one on the top, one on the bottom. Are there any questions?
So they're like adding like together, right?
Yes.
From the top and the bottom. Right?
Yes. The top and the bottom aren't adding together.
Like not together. Like the top one will add together.
The bottoms are adding together. Right. Exactly. Okay. Any other questions? Okay. We'll do another one. So let's do uranium. Uranium 238. So that's going to be, what's uranium? 80, whatever. Let's just say whatever this element is, 80, 238. All right, so we have a chat message. PO is an element, Kaylee. It's polonium. So the elements, so Rn, radon, and the PO at polonium, you can figure those out from the periodic table. So how would you figure out, let's say I didn't have PO, right? Let's say I just had 218 and 84. How would I figure that out? What element it is in the periodic table? Anybody know?
You just check the new atomic number.
Yes, exactly. Good. So you would take the bottom number, which is the atomic number, and you would look at the periodic table, and you'd find 84. And you see that the symbol next to 84 is PO. That's how you would know what element it is. So good job. Okay. So in this example, let's say we have 23880 going through alpha decay. So decay means alpha particle will come off. And then what would be remaining? Anybody want to take a shot?
Mass would be 234. Atomic number would be 78.
Perfect. Good. So 234, 78. And then we look at the periodic table to see what element 78 is. And we can check that out. 78 is PT. 80 is, oh, 80 is mercury. Whoops. So we have mercury going to PT. Which one's PT? Oh, platinum. Duh. I knew that. It's too early for this. So we have platinum, and this is mercury. So That's how you would do that. Any questions on that? Okay, let's move on to the next type. The next type is not alpha decay, but beta decay. So beta decay, same exact principle, but a beta particle comes off. So a beta particle, we know, is a high energy electron. And it looks like this. That's a beta particle. So in this case, we have tritium, which is, if you don't know, it is the radioactive isotope of hydrogen. So it's hydrogen with a mass of 3. So that's where you have 2 neutrons. Normal hydrogen has no neutrons. You could have deuterium, which has 2 neutrons. And then you have tritium, which is really, all the tritium is in space. Not much is on Earth. And this is the radioactive form of hydrogen, where it has it has 2 neutrons, which is too many for it. And then it would radioactive decay. So it would go through a beta decay. And the beta decay would produce helium. One of the neutrons would emit an electron and turn into a proton. But the process by which that happens is complex. But basically, the only thing we have to worry about is the equation. So if we have our helium, or hydrogen, our deuterium, the mass of the starting material, the mass number is 3, atomic number is 1. If it goes through a beta decay, this means it's losing an electron, a beta particle. So the top number doesn't change at all, right? Because electrons are 0. And then the bottom number, you have -1 for an electron. So it would be something minus 1 equals 1. And that something is 2. That's how you would solve this. So we're doing another 2 additions, but you have a negative number here. So you have to keep that in mind to subtract, or however you think of adding a negative number. -1 plus 2 is just +1. Does that make sense? Same exact concept. Okay, so let's do another example with the mercury again. So the mercury, you have, let's say, the same thing we used before, 238. Even though 238 is not an isotope of mercury, who cares? So you have 80 mercury, and it goes through a beta decay. So we're going to have an electron is emitted, and then what would be left over? Anybody want to give it a shot?
So is it 238 set over 79?
Not 79.
It'd be 81 thallium.
Good. Good. So 81 because, wait, where'd my cursor go? Oh, there it is. Okay, so we'd have 238 because the top number is unchanged. And then you'd have 81 because 81 plus -1 equals 80. So that'd be thallium. So T, is it TH or TL? TH, right? TL. Yeah, TL. Okay. All right. So getting the hang of it. So it's just the addition. Okay. Moving on. The next one is called positron emission. So it's just another way of saying decay. Emission, the same thing as decay. So if you emit something, you're losing it. If you decay something, you're losing it. Same thing. So in this case, you have positron. Positron, positively charged electron. In this case, you have fluorine. So it's going to be 18,9 fluorine. It will go through a positron decay or positron emission. So you're going to have 0 plus 1, E. That's a positron. It's a positively charged electron. Plus whatever's remaining. In this case, you'd have 18 equals 0 plus 18. 9 equals 1 plus 8. And we know that atomic number 8 is oxygen. So that's a positron emission. Now, I'm sure a lot of you are thinking, okay, what kind of questions will I expect on the exam? That's a really good question. Now, if I gave you any one of these equations with one thing missing, I would expect you to fill it in. And that goes along with what type of element it is, or what type of radiation it is. So if I gave you this, and I asked you, one, what's missing? And two, what is this equation called? I would expect that of you. I would expect, all right, based on the math, we have 0. This has to be +1. So, oh, I know what that is. That's a positron. And then because it's a positron, this is called positron emission. So I would expect both of those things, what type of equation it is, and to fill in the math. Or if I were to give you, in this equation, we have this, what's missing? So just like we just did, we'd have 18, and then we have 8. It'd be and then identify the element too. Okay. Any questions?
Can we do an example of it?
Okay. And Carla, yes, depending on the element, depending on the number, the bottom number, we know the element. So bottom number is 8. That's the proton number, atomic number. All right, let's do an example. So, I don't know, let's take chromium. Sure. Chromium is 24, let's say 52. So we have 52, 24, CR. And to go through a positron emission. So we have positron, 0, +1, E. So what is left over? Anybody want to guess?
23 on the bottom, so vanadium.
Good,
And 52.
good. And let's double check. That's vanadium, yes. So that'll be V. All right, good. Any other questions on that? No? All right. So the last type is electron capture. So electron capture is a little bit different than the other ones because we're not decaying, we're not emitting, but we're capturing. So it's not going to be losing something, it's going to be gaining something. In this case, the something is the electron. So in this case, we have 12553 iodine plus an electron because you're capturing the electron. 0 minus 1 E. And then doing the math again, you'd have 125 on the top. On the bottom, you're going to have 52 because 53 plus -1 is 52, and that's tellurium. Does that make sense?
Yeah.
Okay, cool. So we'll do one more example. Let's pick one. We'll do hafnium, sure. So that's going to be 178 and 80 or 72. 178, 72. That's going to be hafnium. So we're doing electron capture. So we're going to be adding an electron, which that would be, what would it be?
178 and 71.
Good. Because 72 plus -1 or -1, 71. And the element 71 is going to be this one, the lanthanide, lutetium, whatever it is. Lu. Okay, cool. All right, so let's move on. I think we got the hang of that. And you're going to have some practice on it on the homework. So here is just a chart summarizing the different types of equations. So you have alpha decay, beta decay, which the radiation particles and the products. Gamma radiation, which we didn't go over those. There's no change really. Positron emission also in the products, and electron capture, you have the electron being absorbed. So, yeah. Okay, so we went over this already. Well, there's a difference between chemical and nuclear reactions. So In chemical reactions, all you're doing is rearranging the atoms. But in nuclear reactions, you're rearranging the subatomic particles to make different atoms. That's the key difference. So that's something that's important. Also, nuclear reactions do not involve temperature at all. They're unaffected. Meanwhile, chemical reactions will speed up at higher temperatures. Also, it's the energy absorbed is relatively small, and nuclear reactions involve a large amount of energy, which is why nuclear reactors and nuclear power is probably going to be, once we refine it and figure out and refine good strategies of making nuclear power with little nuclear leakage out of the power plants, then it'll probably be the most used energy on Earth, because it involves a high amount of energy, and there's really little downside. There's no environmental concerns besides emitting radiation, which now, so it's actually an important stat. I think 75 to 90% of the of the nuclear power plants are leaking radiation. So we haven't yet harnessed the power of radiation to make energy in nuclear power plants, but we will. And then once we do, it'll probably be the cleanest energy compared to chemicals, where you're releasing a bunch of stuff in the atmosphere. Okay. So anyway, half-life. So half-life. The half-life of something, and so to keep in mind, these reactions that we just went over are happening all the time to radioactive particles. So if you leave a radioactive chunk of carbon on the table, in 10,000 years from now, it's not going to be just carbon. Half of it will disappear and become a different element. Or not disappear. It would be something different than carbon. So a half-life is the time it takes for 1/2 of the mass sample to undergo its radioactive decay. And this half-life could range from minutes to very unstable particles to thousands of years for more stable radioactive particles. So it's a time. Half-life is a time for half of it to become a different element based on radioactive decay. So here's how this kind of decay would occur. So let's say you have iodine-131. So iodine-131 is commonly used in diagnosing thyroid issues. So you would take iodine, and then a week later you'd go back to the doctor, and you would see the iodine went through its half-life, and you could see how much is remaining in the thyroid, and the thyroid processes iodine. And there's the body, this is a good thing, the body doesn't recognize any difference between different isotopes of an element. That's another key importance of radioactive particles. So, but anyway, in a half-life, let's say the half-life of iodine-131 is 8 days. Your initial sample is 16 grams, or in this case, milligrams. After 8 days, you're only going to have 8 left. After 8 more days, you're only going to have 4 left. After 8 more days, 2 left, and then 1, and then 0.5, and then et cetera, et cetera. Never reaches 0, but it approaches 0. So this is a exponential decay. That's what this kind of equation is called. So any questions on that? That's how half-lives would work. And that's it. Any questions? So things I could ask you would be the half-life of iodine-131 is 8 days. If you have 20 grams of it, how much would be left after 16 days? That's an example. So I'll write this down. You have 20 grams, and the half-life, HL, equals 8 days. How much is left after 16 days? All right, so you start out with 20. How many half-lives are in 16 days? If one half-life is 8, then you have 2 half-lives in 16 days. So this would go down to the first half-life, you'd have 10. The second half-life, it would be 5. So the answer would be 5. Does that make sense?
Can you explain it?
Okay. So the half-life is 8 days. the question's asking for how much is going to be left after 16 days if you start out with 20 grams. 16 days means that 2 of these half-lives are happening. So you have 8 days would be 1 half-life. The next 8 days would be another half-life. So if it's happening twice, meaning the half-life, the time it takes for half of the mass to disappear, or not disappear, but become another element, that's happening twice. So the first time, you'd go from 20 to 10. The second time, you'd go from 10 to 5. So 5 would be your answer.
Oh, okay, got it.
Okay, so here's just some examples of different types of dating that we can do with radioisotopes. So we can determine what the age of a substance is based on using these types of isotopes. And the most common, maybe you've heard of carbon dating for a lot of geological, not geological, well, maybe geological, but a lot of archaeological examples. Like if you have, I don't know, bones, things like that. So from like early humans, stuff like that. So the half-life of carbon-14 is 5,730 years. So what they would do is normally, let's say you have a newly formed item, right? Let's say it's let's say you have bones that are like bones in our body have a certain amount of carbon-14 because we're all carbon-based, right? So our bones are carbon. There's a certain amount of carbon-14, a certain percentage. If we leave our bones for 10,000 years, we're going to have 1/4 of that percentage. So based on the percentage of carbon-14 remaining in that sample, they can figure out very accurately how old the sample is. So that's important. That's one way. Then you have tritium dating, 0 to 100 years. You can figure out the age of wines. That's pretty cool. And then lead, skeletal remains, that's used also. Carbon-14 is also used. And then you have potassium dating. So potassium dating is for like geological, like billions of years old, not billions, but millions of years old. Oh yeah, billions. Yeah, millions to billions of years old. Then you have other things like meteorites, rhenium dating. Then you have uranium, so uranium-238, the half-life is 4.5 billion years, which is about the age of the Earth, or age of the, yeah, right? It's the age of the Earth, 4.1 billion years. Yeah. So it's about the age of the Earth. So like the Earth's crust origins could be determined from uranium-238 dating. So a sample of uranium has a certain percentage of uranium-238. The amount of percent that's there in the sample would tell you how old it is. So those are just some examples. We kind of talked about that. Here we go. So in medical use, we also have examples where we can use half-life to diagnose illnesses. This is called radiation therapy. Well, no, it's not radiation therapy. This is radiation diagnostics. Radiation therapy is when we use radiation to kill cancer cells. And this is very dangerous. So, I mean, you could lose your hair and stuff like that, right? So, but basically, it kills everything. So that's the big side effect. It causes vomiting, nausea, and radiation sickness if you have too much of it. Because yes, it kills the cancer cells, but at the same time, it kills every other cell. And that's the biggest problem with radiation therapy, is that it's not specific to cancer cells, which is why different chemotherapies are more effective, because they at least try to be specific to the cancer cells. But again, there's also problems with chemo. So that's why cancer drugs are in high demand that are specific to cancer cells and won't hurt normal cells. So radiation in diagnostics, we use several of them. And you can imagine the half-lives are very short because we can't be waiting around 1 billion years for a half-life to occur so we can go back to the doctor, right? So some common ones, the most common one is iodine-131. Now, iodine-131, it's used for thyroid diagnoses and therapy. So if you have an enlarged thyroid, what will happen is, or let's say you have thyroid cancer, you would take some iodine. The thyroid processes iodine, and after a week, you'd be able to see how much of the iodine is still there, and you can do an imaging, a radioisotope imaging, and you can actually see the outline of the thyroid with iodine in it. So, or with the radioactive iodine in it. And what that would do is you could see if the thyroid is enlarged or small, or it has different shapes and things. You basically diagnose a lot from that. And then there's a bunch of other ones. So like sodium, locating obstruction in blood flow. That's pretty cool. Pancreas scans. Really, there's a lot of different types of radiation therapies or nuclear medicines, or nuclear diagnoses techniques. So that's pretty cool. Okay. So penetrating power, another important concept. And we kind of mentioned this already, but to get more into detail, alpha particles. So alpha particles are the least penetrating power, and they can, this is a good chart too, but this is better. So alpha particles, you can block them with your hand or a piece of paper. Beta particles, you need a piece of aluminum or a lot of maybe thick clothing, maybe like really thick clothing. And then for gamma rays, you need lead. So the beta particles can go through paper, can go through thin layers of clothing, but something like aluminum or concrete or wood, things like that can block it. But for gamma rays, only lead or thick layers of concrete can block gamma rays, which is why our nuclear reactors are surrounded by lead, and they're surrounded by thick layers of multiple thick walls of concrete. So which in Chernobyl, when we had the meltdown, those layers were all broken and all the radiation was leaked into the atmosphere and environment, and then everybody got cancer, or the animals got 3 heads, and there's mutations. The horror movie Chernobyl Diaries is really interesting. It's really cool if you've ever seen that movie. But anyway, and they have a show on, I think, Amazon Prime called Chernobyl. But I don't know why they put that in the show, because like you kind of know what happens. So I don't know. I never watched it. Anyway, so the penetrating power of the radiation is determined by 2 different things, and really one of them is, and this is all ties into Chernobyl. I guess we use it as Chernobyl. So distance. So if you move away from the energy source or from the radiation source, the radiation decreases. So in the movie Chernobyl Diaries, first they're on the outskirts and there's some radiation, but it's not dangerous. They say, oh, we could be out here for a couple hours and it won't be that bad and we won't get cancer. But then they get stuck there and it's like, oh, we're stuck. And then they're walking around, and they're towards the end, they get really close to the spoiler alert. They get really close to the reactor, and the distance decreases. Therefore, their symptoms from radiation sickness intensify drastically because they're so close to the leaking of the radiation. So that's how distance could affect it. The closer you are to it, the more painful it, or more harmful it is. And then shielding. So if the more shielding you have, the better, and the less harmful it would be. And the more shielding, or sorry, the less shielding, the more harmful it would be. The more shielding, the less harmful it would be. So yeah. Okay. Then you have the atomic bomb. Now for this one, I want to show a video, but we're almost done with the chapter. But at the end, before we split into breakout rooms to begin the homework, I'm going to show a video about atomic bombs and how they work. So we'll leave that for the end. Radioactive fallout. I mean, not really important. So power plants I talked about. So we can use less enriched uranium. So the uranium in atomic bombs is very enriched, meaning it's uranium 235 or 238, or it's 235, but it's less percentage 235. Both of them, the power plants and the nuclear bombs, use 235, but the ones in power plants are just, it's less pure 235, and it kind of leads to a more drawn out radiation emission. So the energy could be drawn out slowly as opposed to in one big burst, which would create an atomic explosion. And then you can have different and chain reactions, which basically what happens when you have an atomic bomb, we'll talk about later or in the video. Okay. So is there any questions really on any of this? I know I kind of briefed through this, but we'll talk about it in the videos. Is there anything right now?